G'day and welcome back to McGrathematics, the YouTube channel that dares to ask the question, what if Eddie Wu was a white dude who was worse at maths? Thank you for joining me. Today I've got a video for my advanced math students, taking them through a guide to how to classify stationary points and sketch curves. Apologies for the email sound just going off in the background, that's really annoying. Okay, so the reason I'm doing this is because Nessa loves to chuck one of these questions in pretty much every year of the HSC. And they're big questions. They usually account for at least 3, sometimes 5 marks. And so it's really important that you know how to work through these questions, showing all you're working properly, setting out properly, and getting those 5 marks. So I'm going to go through a variety of questions today involving an easier, a medium, and then a more challenging level question to give you a full scope of variety of the type of questions that get asked involving this stuff. Before we do that, let's do a little bit of background info. Starting off with our curve over here, which I'm calling f of x. Now this is a cubic curve by the looks of things. Looks like a negative cubic curve. It's got a minimum turning point down here and a maximum turning point up here. Now, first things first, when your first derivative is positive, this is going to tell you where your function is increasing. So for the blue graph over here, between the minimum turning point and the maximum turning point, the curve is increasing because as we go from left to right, the y value is going up. So between these 2 points, the first derivative is going to give us positive values. Everywhere else is going to be decreasing. So we're going to have a first derivative being negative. So on the left here of the minimum turning point and the right here of the maximum point, these are decreasing values and that's going to be a negative first derivative. So that tells us that when your first derivative is equal to 0, that's where you're going to find your stationary points or your turning points. So here at the 0, -1, and up here are where the first derivative are going to be equal to 0. That's super important. So the first derivative tells you whether it's increasing, decreasing, or stationary. The second derivative tells you about your concavity. Wherever your second derivative is positive, this is going to be the curve having concave up values. So here on the left, where we are concave up, this is going to be a positive second derivative. Over here on the right is where the second derivative is going to be negative because that's concave down. I like to think positive is smiley face, so it looks like that, whereas negative is frowny face and looks like that. Now, at some point between these two values, there is a point where the curve stops being concave up and starts being concave down, and that point is called the inflection point, and that's happening right here at 1, 1. Okay, so the way we find that is we look at where the second derivative is equal to 0 to analyze where our inflection points are. Now, the really annoying thing is that the second derivative being equal to 0 is probably going to be a stationary point, but not always. So when we're trying to find stationary points in this video, it's not enough to just see where the second derivative is equal to 0. You have to prove that it's a concave point there by testing concavity on both sides. And it's probably the most annoying part of these questions, and I apologize for maths being tedious. Okay, let's dive into our first question. This one comes to us from the 2020 exam, and it's a pretty friendly one. It's a nice picture as long as you know how to step through, but it is 4 marks that you need to work through by yourself. We have the curve y equals negative x cubed plus 3x squared minus 1, and we want to label the stationary points and the point of inflection. We do not need to find the x-intercepts, which is good because solving this equal to 0 would be a massive headache. Okay, let's start off by finding our stationary points by analyzing our first derivative and seeing where that is equal to 0. So starting off by differentiating, we have the -3 coming down the front, and then taking 1 off the power, that becomes x squared. Bringing the 2 down the front here makes that a 6, and now the power is 1, and the derivative of -1 is just nothing. So there's our first derivative done and dusted. Now to find our stationary points, we're going to see where is that first derivative equal to 0. So usually these questions are designed so that you can do a bit of factorizing. We have a common factor here of 3x squared. We actually might take negative 3x out the front. So factoring that out of the first part leaves us with an x, and factoring negative 3x out of the second part gives us a -2. If you want to make this a little bit more friendly by multiplying both sides by -1 at the start, you can. It's an option. It's still going to give it the same values. It's all good. Okay, now if these two are multiplying and giving us an answer of 0, either the x is equal to 0 or the x is equal to 2 inside the bracket here. So those are our two x values that give us stationary values 0 and 2. So we need to find stationary points, and we have stationary x values, so we need to find our y values. So taking x equals 0 and substituting it into the original equation, so letting x equal 0, we get y equals negative 0 cubed plus 3 times 0 squared minus 1. This gives us a value of nothing plus nothing minus 1, so we get y equals -1, and that's our first point. For the second one, we're letting x equal to 2, once again into the original equation, so we get negative 2 cubed plus 3 times 2 squared minus 1. Calculating this gives us a value of 3. So our first stationary point is at 0, minus 1. And our second stationary point is at 2, 3. Okay, so we've found where our stationary points are. Now let's classify them. Let's figure out whether they are concave up, which is going to be a minimum point, or concave down, which is a maximum point. To classify these, we're going to look at concavity using the second derivative. So our next step is to take the derivative of our first derivative once again. So bringing the 2 down to make negative 6, differentiating 6x to 6, and then we have right there our second derivative. Now we're going to take this function and we are going to sub in our two x values, which are 0 and 2, and we're going to see what we get for our second derivative. When I sub 0 into the second derivative, I get negative 6 times 0 plus 6. This gives me a value of 6, which is, very importantly, a positive number. So positive number implies that it's going to look like a smiley face, which means it's concave up, which means the turning point is going to be a minimum turning point, which looks like this. Okay, so we say, therefore, minimum turning point, and I just draw this little picture here to help me later on. Now let's see what the second derivative is doing when x is equal to 2. So we're going to do f double dash of 2. Subbing it in, we get negative 6 times 2 plus 6. This gives us a value of minus 6, which is crucially negative. Okay, the second derivative at x equals 2 is negative. Negative means frowny face, so it's a maximum turning point, which is concave down. So our second stationary point is a maximum turning point, which looks like this. Okay, so that right there is most of the work done. We've got our stationary points. Now we just need to find our point of inflection, and then we can sketch it to get our last mark. Okay, so moving on, we're just keeping our information there. We've got our stationary points, we've got them classified. Going back to our second derivative, like I said at the very start, if we want to find the inflection point, it's where concavity is changing, and it's where your second derivative is equal to 0. Okay, so we're going to take our function and we're going to let the second derivative equal to 0. We're going to solve this for x by pushing the 6 across to be negative 6, dividing by negative 6, and we get x is equal to 1. Okay, now, before we find the y value, we do, as I said before, we need to check that this is actually an inflection point, because sometimes, very, very rarely, it's not. So the easiest way to do that is I tell my students to do a little table and just do x equals 1 in the middle and just go a little bit to the left and to the right. Sometimes going a whole unit left and a whole unit right can cause you trouble, so I'd probably recommend just going half unit left and right to be safe. Now, when we sub 1 into the second derivative, we get 0. If you sub 0.5 into the second derivative, you get a value of 3, which is positive. If you go to the right and sub 1.5 into the second derivative, you actually get a value of negative 3. So what this table is doing is that it's highlighting that to the left of 1, we are concave up because we're positive, and to the right of 1, we are negative, so we are concave down. This is enough for us to say, yes, concavity is changing, therefore the midpoint here of 1 is an inflection point. Okay, so now we know that x equals 1 is where the inflection point is. Let's find what the y value is so we can go on and do our sketch. So we go to our original function once again, and we let x equal to 1. Subbing that in, we get negative 1 plus 3, take away 1, so we get a value of 1. Also, don't forget, you've got to do the power first before you do the negative, otherwise you're going to get a wrong answer. So this is negative, this is 1 cubed with a negative. Anyway. Okay, cool. So we have 1, 1 as our inflection points, and now we have all the information we need to sketch it. Okay, the original function was a cubic curve with a negative coefficient. Okay, so cubic curves with negatives looks like this. A power of 3 is turning around twice. And I know that it's going from top left to bottom right because it's negative. Okay, so long term it's going in the negative direction. If this was a positive cubic curve, it would be going in the opposite direction and we'd be going from left to right being positive. Okay, so let's get an axis, nice and ready to go. Let's put on our stationary points at 0, minus 1 just there. The other one is at 2, 3, which is just here. And our inflection point in the middle is at 1, 1. So we got this all mapped out. And also, by the way, in the HSC, you don't want to draw little graphs. I know I've drawn a little graph here because I'm trying to fit it onto a slideshow, but you want to be doing your graphs at like at least a third of a page, sometimes half if you have room. Bigger graphs are easy to make neat and are easy to mark. So that's just a tip for you. Okay, so we're going to do this green shape going through these points. We're going to go down here. We don't really care about the x-intercepts. We don't need to label those at all. That's not where the marks are for this question. The marks are for the stationary points and the inflection point and the shape. So we're going to come down here, we're going to curve around at the minus 1, we're going to go up, we're going to come up here and then turn around at the 3 and then come back down and go through the x-axis somewhere. We don't care. So putting it all together, we get a sketch that looks like this. Okay, we've labeled our stationary points, we've labeled our point of inflection, our graph is nice and neat, and that's going to get us 4 out of 4 in the 2020 HSC. So there you go. It all worked out really nice. We had nice coordinates, a nice inflection point. The algebra wasn't too challenging. This is a nice question, and it's really easy to get 4 out of 4 if you know your process and you know how to find your stationary points, how to find your inflection points, and how to classify them. Okay, that's it for example 1. Let's go on to a medium level question, a bit more challenging. This one comes to us from the 2024 HSC. It's still a band 4, but it is a step up in difficulty from the one that we just did because the graph is just not as nice, and it's a power of 4, so it's a little bit higher. Okay, this one's actually a 5-mark question. This was 5% of last year's HSC exam. So yeah, big marks here if you know what you're doing. Okay, we have our curve, x to the 4 minus 2x cubed plus 2. Once again, we're going to find all our stationary points. We're going to check their nature, and we're going to find the points of inflection. Doesn't say anything about intercepts. We can probably just ignore that, hopefully. We'll see. Okay, starting off once again, we are going to find our first derivative, so we can solve that equal to 0, and we can find our stationary points. So taking the derivative of the function, the 4 comes down to become 4x to the 3. The part in the middle becomes 6x squared, and the 2 becomes 0. So there we go. There's our derivative. Now we have something we can solve equal to 0. Like I said again, most of these are going to be factorizable. This one has a common factor of x squared and a common factor of 2. So we can take 2x squared out the front, leaving us with 2x minus 3 in the parentheses. Okay, so out the front, we're clearly getting x equal to 0 for the first parts. For the bit inside, we're going to have 2x minus 3 equal to 0, which means that 2x is equal to 3, which means x is equal to 3 divided by 2, or 1.5 if you're a monster who likes to use decimals. So we have 1.5, aka 3 over 2, and x equals 0 as our 2 stationary values. Now, once again, we want to classify these points. Before we do that, we should find some y values. Let's chuck x equals 0 into our function. Very easy. We're just going to get 0 minus 0 plus 2, so we get y equals 2. So one of our coordinates is 0, 2. Let's check the other one. And like I said, this one doesn't work out to be very nice because when you do 1.5 to the power of 4, you get a pretty gross decimal. Ends up with an answer of 5 over 16 or 0.3125, depending on which of those you prefer. So our 2 stationary points are 0, 2 is the nice neat one, and the disgusting step sibling is 1.5 and 5/16, which is going to be pretty tough to graph, but NES is going to be pretty lenient with how accurate you are with your scale. So don't stress too much about that because we are doing these by hand. They are not going to be perfect. That's just the way things are. Okay, now we have successfully found our stationary points. We can now start classifying them using our second derivative. So we're going to find f double dash by differentiating our first derivative. So the 3 comes down to make 12x squared. The 2 comes down to make 12x to the 1. Okay, that right there is our second derivative. Now we're going to sub in our x values once again of 0 and 3 over 2, and we're going to see what the second derivative is doing. Okay, starting off with the 0. Now when you sub 0 into the second derivative, you get 12 times 0, take away 12 times 0, which is 0. Now that's interesting because normally when the second derivative is equal to 0, it usually implies that it's going to be an inflection point. But once again, the annoying part is we need to check it. So we're just going to dive into another quick little table, and we're going to analyze the concavity to the left and right of 0. So inflection point, perhaps. Let's find out. Here's our table, 0 in the middle for x, which gives us a 0 second derivative. If we go a little bit to the left, we actually get a positive value. When I sub negative 0.5 into this function, I get 9 as an answer. When I go to the right a little bit and sub 0.5 into this function, I end up with negative 3. So what do you know? On the left, it's positive, which is concave up, and on the right, it's negative, which is concave down. This means, hooray, it is an inflection point confirmed. Okay, so it looks something like this. It's a stationary point that's also an inflection point. So the curve is flattening out, but concavity is also changing. Okay, cool. So we found an inflection point. Let's also use the second derivative to classify the second stationary point and see what this one's doing. So making some space now and subbing 3 over 2 or 1.5 into the second derivative. Doesn't get us a very nice value, but all that we care about, actually it does, it gets us 9. That's lovely actually. Okay, so we end up with 9 for the second derivative. 9 is of course a positive number, which means that this point is concave up. Positive means concave up, which means it is a minimum turning point, which looks like this. Okay, flat at the bottom, but it's concave up, so it's a minimum turning point. Okay, so now what we need to do is just summarize a bit. We've got our minimum turning points here. We've got our horizontal inflection point at here. Now the question said finding the points of inflection. Now that's definitely implying to me that there's more than one inflection point, and we've only found one of them. So to get our 5 marks, we need to find the other one to make our sketch as perfect as can be. So to find the other point of inflection, we are going to go back to our second derivative, and once again we are going to solve this equal to 0. Okay, inflection points typically occur where the second derivative is equal to 0. All right, so setting this equal to 0, we can factorize out a 12x, leaving us with x minus 1 inside the brackets. This expression is going to give us two answers. The first one is x equals 0, which is obvious because we already knew that. We already have an inflection point at 0, 2. The other one is when x is equal to 1 is the solution inside the parentheses. So x equals 0 and x equals 1 are probably where we're going to get our stationary points, our inflection points, sorry. Okay, but as always, I know it's very frustrating, but we've got to check it, okay? We're going to take x equals 1 and we're going to look to the left and to the right. Now, we already did these today. 0.5 already got us a -3 for our second derivative, and 1.5 got us a 9 once again. So again, this table is all you need to show that we are demonstrating understanding that for an inflection point, to check it, we need to check the concavity is swapping both sides. Negative on the left, positive on the right. So concave down to concave up. Concavity is changing. This is indeed an inflection point. So that's enough to be confirmed. Now we're just going to finish it off by finding the y value that goes along with x equals 1. So we actually know where this inflection point is. So we'll go back to our function, original function, and we'll let x equal to 1. So we have 1 to the 4, take away 2 times 1 cubed plus 2. Okay, this calculation gives us a value of 1. So that means our inflection point is at x equals 1, y equals 1. So 1, 1 is a POI, a point of inflection. Okay, so we have our we have a minimum turning point, we have a horizontal inflection point, so a flat inflection point, and we have just a regular inflection point, which is not flattening off at 1, 1. So let's get onto a graph and try and piece this all together. Let's make some space. Okay, here's our graph. We have 0, 2, just here for our horizontal inflection points. We have 1, 1, which is here, which is our other inflection point, and our minimum turning point is at 1.5, 0.3125. Obviously, I've done this digitally, so yours may not look as beautiful as this, but that's okay. As long as you're showing the information that you've proven with the calculus, you're going to get the marks here. Okay, we have a positive power of 4 cube. What that looks like is this. It's like a W shape. Okay, so our power of 3 was turning around twice. Our power of 4 can turn around up to 3 times. What's important here is that because it's positive, the endpoints are both pointing up. If this was a negative x to the 4, those endpoints would be pointing down and it would be an M rather than W. Okay, so to make this shape sort of work with this graph here, we're gonna have to come down from the top here. We're gonna have to wiggle through at 0, 2 because it's an inflection point. So come down, we're gonna wiggle through. We're then going to inflect. So we're gonna change from concave up to concave down at the 1, 1. And then the point down here is our minimum turning point. So we're gonna go through here, turn around, and then come back up. So we have coming down here, wiggling through, passing through 1, 1, turning around here, and then shooting back up to finish our curve, which looks a bit like this. Okay, here is the provided solution from NASA, which is obviously very neat, but if yours looks something like this, and you've got all the information, including the inflection point here, which is a turning point, the inflection point, sorry, which is the stationary point, the inflection point here, which is non-stationary, and the minimum turning point down here, that's where you're gonna get your 5 marks. And you'll see that we didn't even need any x-intercepts because we aren't touching the x-axis at all, which is why the question didn't mention them at all. So if it wants you to find the x-intercepts, it'll tell you. If it doesn't want you to find the x-intercepts, it won't tell you. So because this question didn't mention x-intercepts, it's a good hint that you're not going to need them at all. Okay, so that right there is our graph for 5% of the 2024 HSC. Like I said, quite often these are designed to be nice questions. This one with the gross coordinate down here is pretty rare, but they are still possible. So a lot of variety is possible in the HSC, and we're just trying to do our best to prepare for whatever's coming. Okay, speaking of, we're going to finish off with one more question, which is an upper level question. Same concepts, but applied to a bit of a more hectic case. Finishing off with example 3. This one is, I feel like that's not from 2024. That's because they wouldn't do 2 in 1 year. Let me check that and post in the comments whether that's a typo or not, because it feels very unlikely. Anyway, this is a band 5 level question. That is true. We have a function which is e to the negative x times sine x. And part A for 3 marks. Again, this is a 5 mark question. This is 5% of some exam paper, probably not 24. I'll get back to you. Okay, find the coordinates of the stationary points of the function between 0 and 2 pi. You do not need to check their nature. Okay, that's going to save us a lot of work. Once we've done that, we're going to use part B, which is to sketch it without any further calculus. We want to find some intercepts. So a fair bit of work here. Let's start off by finding the coordinates of our stationary points by seeing where our first derivative is equal to 0. Before we get there, we've got to get our derivative, which for this function is going to be a little bit challenging. So let's make some space. Find the coordinates of the stationary points. Okay, we have f dash x. What we have here for our function is a product. We have e to the negative x multiplied by sine x. And when you want to differentiate a product, you've got to use the good old-fashioned product rule. Product rule basically says take each component of your product and just differentiate them one at a time while leaving the other part alone, and then sum together the result. So let's apply this to our question. We're going to start off by leaving the e to the negative x alone, and we are going to differentiate the sine, and the derivative of sine x is cos x. So the first part is e to the negative x left alone, multiplied by the derivative of a sine x, which is cos x. Now we're going to do a plus, and for the second part, we are going to leave the sine x alone, and we are going to differentiate the e to the negative x. And a reminder, to differentiate e to a function, you leave it alone, you leave it as is, but you multiply it by the derivative of the power. And the derivative of negative x is negative 1. That's why my e to the negative x is being multiplied by negative 1. Okay, so that's our product rule in show. We can tidy it up a little bit. We have e to the negative x cos x, take away e to the negative x sine x. All right, so there is our first derivative. Now we need to find our stationary points by seeing where is this equal to 0. Okay, so fortunately, both of these components have an e to the negative x as a common factor. So we can actually factor that out the front and have e to the negative x times cos x minus sine x. Now, analyzing where this is equal to 0, it's really important to know what the graph of e to the x and the graph of e to the negative x looks like. Because if we're trying to see where is e to the negative x equal to 0, if you draw a little graph, what you're going to see is that e to the negative x is never 0, okay? This is a exponential curve, exponential decay, because it's turned around by the negative x, and so it's approaching the x-axis as we go to infinity, but it never crosses it, it never touches it. So from this graph, we can say that e to the negative x equals 0 has no solution, okay? E to the something is never equal to 0. So if we're trying to solve this equation and see where it's equal to 0, we can only really solve the inside, which is the cos minus sine. So we're going to see where is cos minus sine x equal to 0. All right, the way we're going to do that is we're going to add the sine x across the other side. And now a cool trick here is we can divide both sides by cos, because on the left, when you divide cos by cos, you get 1. And on the right, we get sine divided by cos, and sine divided by cos is equal to tan, okay? So you could have gone up here and said, all right, I know cos and sine are equal to each other when the angles are complementary, like they add to make 90, but I personally think this process is a little bit more straightforward of turning into a tan equation. Okay, there's a lot of talking. All right, moving on now. Tan x equal to 1. Where does that happen in 0 to 2 pi? Well, it's positive, and we know that tan is positive in quadrants 1 and quadrants 3. We know that tan 45 gets us a value of 1. So we're going to do 45 in quadrant 1, and we're going to do 45 in quadrant 3. And the way we do quadrant 3 is we do 180 plus 45. Okay? Here are our two solutions for this equation. If that makes no sense, you should watch my trig equations videos because I've got a couple of them for advanced. Anyway, we're going to turn this into radians because this question is working in radians, and we're going to say 45 degrees is pi on 4, and we're going to say 225 is 5 pi on 4. Okay, we're almost done. We have the x values of our stationary points. Now we just need to find our y values by subbing these two x values back into the original function and getting y values. So let's make a bit of space, and let's see what f of pi on 4 is. It's going to be e to the negative pi on 4 sine pi on 4. And now sine pi on 4 is sine 45, which is exactly equal to 1 over root 2. So this is equal to e to the negative pi on 4 divided by root 2. If you want it, you can then use the fact that a negative power can cross the fraction line and go on the bottom. So this is the answer that was provided by Nessa. You don't have to do that if you want to, but you can put the e to the negative pi on 4 on the bottom of the fraction by making it e to the positive pi on 4. Okay, there's one of our stationary points. The other one is where x is equal to 5 pi on 4. So we take this x value of 5 pi on 4, sub it into our function, and we get e to the negative 5 pi on 4 sine 5 pi on 4. Okay, so sine 5 pi on 4 is sine 225, which is the exact same value as sine 45, but because it's in quadrant 3, where sine is negative, this time we get negative 1 over root 2. Okay, so same value as before, but it's in a negative quadrant for sine. So this gives us the same answer as before, except the power is now 5 pi on 4, and we have a negative out the front. Okay? So here's our y value. Again, if you want to, you can put the e on the bottom of the fraction by making it positive, but that is optional. Okay, so very similar as before, except our power is 5 pi on 4, and it is negative out the front. Okay, and those two things in green are our two stationary points, and that gets us 3 marks. As the question said, we do not need to check their concavity, so we don't need the second derivative, which is good because that would be an absolute freaking nightmare. So there's part A done for 3 marks. Let's now go on to part B, where we try and sketch this thing and try and make it look half readable. It's a really, really tough sketch. Okay, without any further calculus, sketch the graph showing stationary points. We've already found those. Here they are. Ta-da. I just did some decimal approximations just to give you an idea of where these guys are going to be on our graph. We're going to have 0.32, which is going to be up, and we're going to have negative 0.01, which is just slightly below the x-axis. Okay, there's our stationary points. We also want to find our intercepts if we want to find a graph of this. So let's find our intercepts. The way you find the intercepts, or the x-intercepts of a function, is you see where it's equal to 0. So we want to see where e to the negative x sine x is equal to 0. As we've already explained today, e to the negative x can never be 0, so we can just get rid of this, or we can divide by e to the negative x. We just want to see where sine x is equal to 0, and so we just want to picture our sine graph between 0 and 2 pi. Sine is equal to 0 at 0, and then pi, and then 2 pi. Okay, so just thinking of the graph of sine x, here is where sine x passes through the x-axis. 0, and then pi, and then 2 pi. Okay, so we have our 3 x-intercepts. We have our 2 stationary points. Let's put them onto a graph and then try and draw a graph, as I said, that kind of is readable. Starting off with our 3 x-intercepts, 0, pi, and 2 pi. Once again, we are just sketching from 0 to 2 pi, so that's all good. Now, our first stationary point is at pi on 4, and like I said, 0.32 doesn't have to be really precise with your scale, but we need to show that this one is up, and we need to show that our second stationary point is at 5 pi on 4, which is just here, and it's negative 0.01. So it is just below the x-axis. It is slightly negative. Again, scale doesn't need to be perfect. But if we've done all this correct so far, we can start to see the shape of this thing. We're starting at red, we're going up to the green point, and we're turning around. Then we're going down, we're passing through red, and then we're turning at the green dots, and then we're getting really close to the x-axis, and then eventually touching at 2 pi. So like I said, a really challenging graph. Starting up here, going up, turning around, passing through, slightly turning around, and then turning back towards the red dot here. That leads us to this picture right here in blue, and here is the solution that was provided by Nessa, which looks a little bit better than mine. As always, really good practices involve making your axes nice and clearly labeled with the pi and the 2 pi that we wanted to show. Label your stationary points that you found in part A, and always a good idea to label your graph as well, but I'd say that wouldn't be losing you any marks. Anyway, that's how you graph e to the negative x sine x using calculus in the advanced maths course. Wasn't that fun and not horrific at all? I enjoyed that. All right, hopefully that gives you some idea or some more confidence in sketching curves and finding stationary points and classifying them, using all the derivatives and tying it all together, and gave you some tips to smash these questions if they come up in your exam, which, like I said, they probably will. They're there pretty much every year. You can't escape them, so it's time to get good at them. Okay, thank you so much if you made it to the end of that and got some value out of that. I appreciate you watching, and if there's any other concepts in advanced maths you could use a lesson on, please let me know and I'll see if I can add it to the roster. But that's all for this week. Thanks for watching, and I'll catch you in the next advanced math lesson. Bye for now, not forever.